Hello, this is my Lab 2 for Modern Physics 1. In this lab, we will be observing the motion of a falling object and comparing it to the models with and without drag. We're using Newton's second law of effective motion. We'll also observe how drag affects the motion of the object and how we can find the drag to better predict the motion of our object. We will use Newton's second law as shown here. V final equals V initial plus F net over mass times delta T. And the position function is when just final position is found by getting the initial position plus the final velocity times delta t. Fnet will be calculated using the weight force plus the force of the drag. The weight force is going to be the minus of the mass times the gravity coefficient, which is 9.8 for Earth. And this j hat vector gives it direction and makes it into a vector form. Force of drag, we use b as a constant for drag of the object, and for our object we found that to be 0.029. We find the magnitude of the final velocity vector, squared that, and j hat also helps give it direction. This was the video I used. It's just a falling baseball, and then we put that in the tractor and put that into our graph, which we'll see later. And we also made a model now with the code. The ball's mass, 0.145 kilograms, standard baseball size. Our ball started from rest, of course. There's our gravity coefficient and our drag coefficient, which we determined with trial and error, which we'll get to later. The time was 0.53 seconds overall. And to calculate this, we coded in our equations for Fnet, which we saw earlier. That's, the weight minus ball, gravity, j hat, and all that. And then we also coded in Newton's second law and the position update function. For our error scale, I went with 0.7, as I found that's what got me the force with magnitude of 1 meter, getting a 1 meter long error. And then when we run that code, we get this little thing, and let's get this visualization. And all that gives us this graph. Now, as you can see, when we model it without a drag, the model starts to get a bit separated from the observed, especially towards the end of the time where it really starts to separate. Now, when you model it with drag, though, it's very accurate. As you can see, there are some discrepancies around the middle. That's probably due to small mistakes in the video formatting, small mistakes in using tracker. It's also probably due to maybe not having the exact drag coefficient. We kind of had to guess and check that by basically taking our model without drag and and changing the drag coefficient until we had the same final position as our observed. And so that leaves room for a bit of error there. Now, what does it mean? Do any of the models predict terminal velocity? They don't actually predict terminal velocity because the fact that the slope of both lines is changing, and so the velocity is as well. If given enough time, though, these lines will eventually go linear, and that's when we'll see the terminal velocity. And our what if question, would the object have the same terminal velocity if it was thrown downwards? Yes, it would. Terminal velocity is basically a product of the drag force equalizing the weight force. And when both are equal to 0, you have your object is equilibrium, and therefore it has a constant velocity, the terminal velocity. If it's thrown down, it's just going to get there maybe a little bit faster. Here's our actual velocity versus time. The orange line is our object, but with a starting velocity of 3 meters per second. So, as you can see, they both kind of trend towards the same area, but the orange line will probably get there before the blue. And that's about it. Thanks for listening.